NVIDIA's Vera Rubin platform is ramping into full production. The obvious way to read that headline is simple: NVIDIA has built a faster system. The GPU race is accelerating again, and the companies with the best chips will keep the advantage.
But that misses the more important question. It is not only how fast Rubin is, it is whether an AI factory can get usable power on time, because the best hardware in the world can still sit idle if the data center cannot connect to the grid.
So the next AI bottleneck may not be the chip itself, it may be the ability to turn electricity into operating compute.
Exactly. Power-ready capacity, electricity at the right site, connected on a realistic timeline, ready to become live AI capacity. AI demand is scaling at software speed. AI factories can only be built at infrastructure speed.
And that gap is where the value shift begins.
This is value shift. The headline is temporary. The value shift is not.
Let's start with Rubin. Most people still think about NVIDIA as a chip company. What is different about the way the company is describing this platform?
NVIDIA is not presenting Vera Rubin as one faster GPU inside one server. It is presenting Rubin as a platform designed for an AI factory. Multiple racks are built to work together as one integrated AI supercomputer. Computing, storage, networking, and inference acceleration are coordinated as one system. But the component list is not the most important part. The design logic is, NVIDIA is no longer talking only about the performance of a chip. It is talking about the performance of an entire infrastructure system. The company is also emphasizing a planning framework that brings computing, networking, storage, power, cooling, and operations together. Two phrases stand out: tokens per watt and time to first production.
Those phrases change the frame. Tokens per watt asks how much output you can generate inside a power limit. Time to first production asks how quickly a planned facility becomes an operating facility. Neither question is answered by buying a faster chip alone.
That is the point. The first phase of the AI boom was easy to understand. Companies wanted more advanced chips. Supply could not keep up. Access to GPU capacity became a strategic advantage. That phase is not over. Chips still matter. Memory still matters. Supply chains still matter. But once a company can buy a more powerful system, it still faces a harder physical question: where can it plug the system in?
A chip can improve on a digital roadmap. A data center cannot connect to the grid with a software update. That sounds like the central conflict.
It is. AI demand is scaling at software speed, but AI factories can only be built at infrastructure speed. The International Energy Agency has warned that around 20% of planned data center projects could face delays unless grid-related risks are addressed. It also notes that new transmission lines can take 4 to 8 years to build in advanced economies. Wait times for critical components such as transformers and cables have doubled in the past 3 years.
So even after the hardware is available, a company may still be waiting for transmission capacity, transformers, permits, construction, and a grid connection. The equipment can arrive before the infrastructure is ready.
And when those two clocks move at different speeds, value begins to move with the bottleneck. The question is no longer only who can get the chips. The next question is who can turn electricity into live AI capacity faster than competitors. The International Energy Agency estimates that global electricity consumption from data centers could more than double by 2030, reaching around 945 terawatt-hours. That is slightly more than Japan's current annual electricity consumption. In the United States, data centers are projected to account for nearly half of electricity demand growth through 2030.
Those forecasts are large, but they are not guarantees. AI adoption could slow. Efficiency could improve faster than expected. Some announced projects may never be built.
Correct. These forecasts do not prove one exact future, but they still tell us something important. The direction of pressure is changing. AI is becoming a physical infrastructure story. And if you remember one phrase from this episode, remember this one: power-ready capacity.
Let's define that carefully. A region may generate a large amount of electricity. That does not automatically mean a new AI campus can use it. Electricity on paper is not the same thing as operating compute.
Exactly. Can the site secure a grid connection? Can the transmission system carry the load? Are transformers available? Can the operator obtain permits? Can the facility be built and energized on time? Can the system remain reliable when workloads rise and fall? Only then does electricity become usable AI capacity.
So the real constraint is narrower than how much electricity exists. It is how much power can reach the right place, through the right infrastructure, within a commercially useful timeline.
Think about a fast-growing restaurant chain. At first, the scarce asset is the chef. Without the chef, there is no product. Then the chain improves the recipe, standardizes the kitchen, and trains more staff. Each location becomes more productive, but eventually, the expansion constraint moves somewhere else. The chain still needs the right building, it needs permits, it needs utilities, it needs a working kitchen, and it needs each location to open on time. The chef still matters, but the bottleneck has moved.
That is a useful analogy because it avoids a false choice. The claim is not that chips suddenly stop mattering. The claim is that faster chips do not automatically create faster deployment. Once one constraint becomes easier, another constraint can become more valuable.
And when a bottleneck appears, bargaining power may begin to move. During the first phase of the AI boom, access to advanced chips created leverage. During the next phase, leverage may increasingly come from shortening the path between equipment delivery and operating capacity. That advantage may come from a site with available grid capacity. It may come from a location with land, fiber, and approvals already in place. It may come from an operator that can coordinate power, cooling, construction, and deployment without losing years to redesign. Or it may come from a system that can generate more output inside a fixed power envelope.
But we should be precise, this does not mean every power project becomes strategically valuable, and it does not mean every announced data center will reach full scale.
No, the scarce asset is electricity with a credible path to operation. A takeoff slot at the right airport has value because it gives an airline access when demand is there. Power-ready capacity may begin to work in a similar way. The value is not only in owning a resource, the value may come from controlling access to that resource when the market needs it.
So, the strongest position may not belong only to the company with the fastest chip. It may also belong to the operator or location with the shortest path from equipment delivery to revenue-producing capacity.
That is why NVIDIA's language matters. Tokens per watt, time to first production. The AI factory as a coordinated system. Those are infrastructure metrics. They reflect a market where the cost of delay is becoming more visible. A rack sitting in a warehouse is not productive capacity. A data center waiting for a transformer is not productive capacity. A site stuck in a connection queue is not productive capacity. The value is created when the system goes live.
Now let's take the strongest counterargument seriously. What if efficiency solves the problem? New chips can generate more output from each watt. Software can become more efficient, models can become smaller, workloads can move across locations or across different times of day. Companies can become more selective about which AI tasks are worth running.
And some ambitious data center announcements may never reach full scale. This is not a weak objection. It may decide whether power-ready capacity becomes a defining bottleneck or only a temporary constraint. The International Energy Agency has noted that electricity use per AI task is falling rapidly. If efficiency improves faster than demand grows, the power bottleneck could loosen. If AI adoption slows, the build-out could disappoint. If many projects turn out to be speculative placeholders, the apparent shortage could be overstated.
The reversal risk is real, but efficiency does not always eliminate demand. Sometimes lower costs create new uses.
Exactly. When the cost of computing falls, companies find more uses for computing. When the cost per token declines, more AI workflows may become economically viable. More AI agents may run for longer periods. More companies may automate more tasks. More products may embed AI into everyday operations. So the key question is not whether efficiency improves, it almost certainly will. The key question is whether efficiency improves faster than demand expands.
That gives us a clean future value map for the next 6 to 24 months. Start with the base case.
The power bottleneck remains persistent but uneven. Advanced chips continue to improve. AI factories become more standardized, but grid connections, equipment lead times, permits, and local infrastructure remain slow enough that speed to power becomes a competitive advantage. In that scenario, the advantage does not automatically go to the companies announcing the largest capacity targets. It goes to the operators and locations that can turn plans into operating capacity with the least friction.
What changes in the acceleration case?
Demand from AI agents grows faster than expected, inference workloads expand, reliable power demand rises faster than efficiency can offset it. Competition spreads beyond chip procurement into grid access, site design, and more flexible use of available power. The bottleneck becomes more visible, and the value of power-ready sites rises.
And the reversal case is the opposite. Efficiency gains outpace demand growth. AI adoption becomes more selective. A meaningful share of announced projects is delayed, downsized, or canceled. Grid reforms move faster than expected. Additional power supply and grid capacity arrive quickly enough to ease the constraint.
In that scenario, power-ready capacity still matters, but it does not become the defining bottleneck of the next phase.
So what should we watch if we want to know which scenario is actually unfolding?
First, connection timelines. Are new AI campuses moving from announcement to energized operations, or are they sitting in queues? If those queues shorten materially, This thesis becomes weaker. Second, company language. Are companies still competing mainly on GPU counts, or are they increasingly talking about tokens per watt, time to power, grid flexibility, and time to first production? Third, project locations. Do developers keep crowding into the same major data center clusters, or do they move toward regions with available power, land, fiber, and faster approvals? And finally, the efficiency equation. If computing output rises much faster than electricity demand across several consecutive updates, the power bottleneck may loosen. But if lower costs unlock even more usage, the constraint may become more visible.
Then the conclusion is not power wins and chips lose. That would be too simple. Chips remain essential, but the competitive question is widening. The advantage may increasingly depend on whether a company can convert a powerful system into operating capacity before competitors do.
The AI build-out may be moving from a component race toward a conversion race. The scarce capability is increasingly the ability to convert electricity, land, equipment, and approvals into live AI capacity. Vera Rubin is the headline. Power-ready capacity is the value shift.
And the bottleneck will not stay in one place forever.
In the next episode, we will look at which regions are actually positioned to build AI factories faster, and which regions may fall behind. Subscribe to Value Shift if you want to track where bottlenecks, bargaining power, and strategic control move next. The headline is temporary. The value shift is not.